If you think you know how the universe is going to end, you're probably wrong. That's because no one knows for sure what the future has in store for us, and because, from big crunches to big rips, from cyclic revivals to periods of infinite darkness, the options appear limitless. But that's not to say that forecasting the end of the universe is beyond the capacities of science. By learning more about the universe around us today, we can uncover what will help us predict its ultimate demise. I'm McColgan and you're watching Astrum. Join me today on a journey to the future of the universe. A future where there are no longer any planets or stars or galaxies. No longer any atoms or molecules or life. A future where the universe is lying on its deathbed. How long do we have until that future is here? And is there an afterlife for the universe? These questions might sound impenetrable, but their answers lie in our understanding of the most familiar force of nature, gravity. Ordinarily, gravity is an attractive force that slows down objects trying to move farther apart or speeds up objects moving closer together. That's why, before dark energy was discovered, astronomers assumed our expanding universe was being slowed down by gravity over time. They even came up with a parameter called Q to measure the rate of this deceleration. But at the close of the 20th century, measurements of supernovae revealed that Q was actually a negative number. The universe wasn't decelerating at all, it was accelerating. This acceleration is fundamentally tied to the type of matter and energy contained in the universe. If the energy of ordinary matter gives rise to gravitational pull, it must take a very different form of energy to explain the gravitational push accelerating the expansion of our universe. We call this form of energy dark energy. The tricky thing is, we don't know what dark energy is exactly, or where it comes from. And yet, the very fate of the universe is tied to its identity. Depending on the nature of dark energy, the accelerated expansion of the universe can grow stronger, settle down, or even reverse course. Rather than making a video on just one of these fates, we've decided to collect them all into one big flowchart to serve as your one-stop guide to the end of the universe. At the top of the flowchart is what dark energy is, and at the bottom is how we all die. Most cosmologists would agree that dark energy is likely to fall into one of two main categories. First, the most popular theory is that dark energy is the energy of the vacuum itself. Second, the leading alternative is that dark energy is the energy of new fields in the universe that we simply haven't discovered yet. Since fields are just a way to represent collections of particles, this would mean that dark energy is made from a new form of matter, new types of particles, beyond electrons or quarks or anything else we know of today. From these two categories, our flowchart is going to branch out into theories of dark energy that are wildly different from each other and predict all sorts of catastrophic futures. On the vacuum energy side, we need to consider whether the vacuum itself is stable or whether it can jump into a state of even lower energy through a process known as quantum tunneling. A stable vacuum is by far the simplest scenario. It means the dark energy will continue to exist for an eternity in the same form it takes on today. Our universe will accelerate forever, growing infinitely larger and colder in what's called the Big Freeze. The good news is, you wouldn't notice anything changing here on Earth, or even throughout the Milky Way, since there's enough mass concentrated in this small region to counteract the gravitational repulsion coming from dark energy. But if you zoom out beyond that, you'll notice that distant galaxies are being accelerated away from our own in all directions, eventually crossing a threshold known as the event horizon. Just like with a black hole, once you cross this point, you can no longer communicate or interact with the world you've left behind. That means that, one by one, we'll lose contact with all galaxies beyond the local few where gravity is strong enough to keep us close. All that will remain of them is a dimming, reddening light from the moments before they cross the event horizon. Eventually, this light will become so faint that it too will be unobservable, and future generations of astronomers, billions of years down the road, might have no idea that anything ever existed in the universe beyond the Milky Way. If you're wondering what will become of the stuff inside the Milky Way, it dies a relatively boring death. The second law of thermodynamics says that systems will always tend towards a state of higher entropy. When stars fuse hydrogen into helium and emit light as a byproduct, when planets heat up and winds soar across the atmosphere, and even when you eat a carrot and wait for it to come out the other side, all of those processes increase entropy. But the entropy of the Milky Way can only grow so large. Eventually, stars will run out of hydrogen to fuse, planets will be left to freeze, winds will abate, and there will be no more carrots left to digest. Matter will have nothing to do but collapse into black holes, and black holes will evaporate into a pool of radiation. What we once called the Milky Way will be in a state of total thermal equilibrium. Nothing will be happening. There will be nothing to happen. This fate that awaits the Milky Way is sometimes called heat death. Not because it's hot, in fact it will be quite cold, but because there will be no more heat flow, no more temperature gradients, no more transfers of energy from one place to another. Admittedly, it might take a while to reach heat death. Some estimates place it at 10 to the power 106 years away, or 10 to the power 96 times the current age of the universe. But if dark energy really comes from a perfectly stable vacuum, then there will be no avoiding it. Heat death is coming. There is one possible silver lining at the end of this story, however. It has been conjectured by Sir Roger Penrose, a Nobel laureate and brilliant physicist, that heat death might not be the end of our story, but merely a new beginning. In his model known as the conformal cyclic cosmology, Penrose proposes that the radiation-filled universe in the infinite future will be indistinguishable from the state of the universe at the Big Bang, and indeed may be one and the same. Each eon of infinite expansion in this model merely leads to a new Big Bang and a new cycle of cosmology. There isn't much evidence in support of this hypothesis as of yet, but it may be a source of hope to cling on to if our universe ends up heading towards a big freeze. You and I would not survive, but maybe the universe could, and at least that's something. If the idea of a big freeze scares you, I got some good news and some bad news. The good news is that there are reasons to believe that even if dark energy comes from the vacuum, that vacuum state might not last forever, meaning we might not be headed towards a big freeze at all. One reason to doubt the stability of the vacuum comes from observation of the Higgs field. Current measurements from CERN indicate that the Higgs might have a lower energy vacuum state than the one we live in, though it could take something like 10 to the power 100 years to tunnel into this preferred vacuum. To paint a mental picture of how this all works, we can imagine an apple falling off a tree, hitting our friend Isaac on the head, and rolling off into a small dip in the grass. A short distance away, there's an even bigger dip, which the apple would absolutely be drawn towards, if not for the barrier blocking its path. Classically, the apple is stuck, but quantum mechanically, the apple can and will tunnel through the barrier into this low energy state if you just wait long enough. The Higgs field works the same way, with its different vacuum states corresponding to the different dips in the grass. A second reason to doubt the stability of the vacuum actually comes from string theory. While string theory hasn't made any quantitative predictions, it's given us some pretty strong hints that stable vacuum states with positive energies are really hard to come by. String theory also predicts the existence of new fields that could conceivably tunnel to different vacuum states much faster than the Higgs, say within the next trillion or even 100 billion years. Here comes the bad news though. If we live in a metastable vacuum that can decay at the whim of quantum mechanical fluctuation, we've got bigger things to worry about than the big freeze. Quantum tunneling into a more stable vacuum won't just affect the expansion of space, it can also fundamentally alter the properties of particles and the laws of physics governing our universe. If the Higgs field falls into a new vacuum state, ordinary particles like protons and electrons will have completely different masses, and atoms and molecules as we know them will cease to exist. Or, if we tunnel into a new vacuum in the string theory landscape, our universe might suddenly contain new particles we've never seen before. In either case, life on Earth would all but certainly be toast. As for the universe as a whole, in this scenario we can't predict its fate more precisely without more information about the new vacuum we fall into. Let's step back and take a look at the other side of the flowchart, where dark energy comes from the presence of new fields rather than the vacuum. There are different ways in which fields can evolve over time, which would dictate the future trajectory of our universe. Unlike vacuum states, which would have perfectly constant energies between tunneling transitions, fields can continuously gain or lose energy over time. Just like a ball rolling across a rough patch of grass, fields experience friction as they evolve, so it's most natural to expect their energy to decrease. But physicists have shown it's possible to have exotic types of fields called phantom dark energy that overcome this friction and actually gain energy over time. These exotic fields wreak absolute havoc on the universe. Because their energy is growing everywhere and all the time, they eventually overpower the energy from all other forms of matter, even within the Milky Way. This increase in energy heats up the entire universe, fully reversing course from all the cooling the universe has done over the past 14 billion years. In this scenario, the expansion of space doesn't just continue to accelerate, but it accelerates so fast that any region of space will grow to infinite volume in a finite time, maybe even just a few billion years from today. And if you want to call for help, that gets increasingly harder, as the cosmic event horizon we spoke about earlier will shrink down to the size of our galaxy, then our planet, then our home, and then us. As this is happening, the repulsive gravitational effects of phantom dark energy grow ever stronger, ultimately tearing apart all of the molecules, atoms, and nuclei in the universe into their constituent parts. Then we hit the singularity. This new kind of singularity, where the universe is infinitely big and hot rather than infinitesimally small and hot, has been called the Big Rip. But I'm still hopeful that this grim ending from phantom dark energy exists only in the minds of theorists, while the real dark energy in our universe behaves more peacefully and loses energy over time. So what would fate have in store for us then? Here's where our flowchart starts to get a little messy, because there are so many different ways a field can evolve over time. There are two main questions that have to be answered to predict the fate of the universe in this scenario. First, can the dark energy field have negative potential energy? And second, does the field's energy change slowly or quickly? If the field's energy is always positive and it loses energy very slowly, it would hardly be distinguishable from vacuum energy. In this case, it would be headed towards another big freeze. On the other hand, if the field's energy is drained away very quickly, the universe would soon have no dark energy left at all. It would stop accelerating, and its future would depend entirely on its spatial curvature, or the shape of the universe itself. A flat or open universe would eventually evolve towards heat death, but there would be no cosmic event horizon to prevent us from communicating with galaxies as far as the eye can see. This may be the most peaceful of all the possible futures for the universe. On the other hand, a closed universe would eventually stop expanding, reverse course, and collapse back in on itself, which sounds less peaceful. This kind of recollapse is known as a big crunch. Having a closed universe is just one of two paths that can lead to a big crunch. The other way to see our Milky Way crushed to smithereens is for the dark energy field to reach a negative potential energy. At that point, it will only be a matter of time before the universe stops expanding and begins to contract. During this contraction phase, gravity turns cosmic friction into what theoretical physicists call cosmic anti-friction, speeding up the field's evolution and giving it more energy rather than draining it. If the field gains energy slowly, there will be plenty of time for the universe to recollapse and experience a full-on big crunch. On the other hand, if the field gains energy fast enough, the universe could reach a temperature mimicking conditions at the Big Bang at a rate so fast that this would all occur before the Milky Way is even predicted to collide with Andromeda. Even though space does contract in this scenario, it doesn't crunch. In fact, the amount of contraction is hardly noticeable by the time Earth turns to toast. So, what happens next? Models suggest that if the universe reaches extremely high temperatures while contracting, it could be forced to transition into a new phase of expansion, where it has time to cool off once more. This transition is called the Big Bounce. In fact, the universe could go through a big bounce following a big crunch too. These scenarios open the door to a new type of cyclic universe, entirely different from Penrose's idea, which we've discussed in a previous video, in which the universe goes through an infinite sequence of expansion, cooling, contraction, and reheating over and over again. In this picture, even our Big Bang 14 billion years ago could have actually been a big bounce, connecting our own cycle of the universe to all those that came before it. This wraps up our master flowchart for all the different ways the universe could end. It could freeze to death, be ripped to shreds, be crushed to oblivion, or simply heat up so quickly that it bounces into a brand new life cycle. We might not have any certainty yet, but even just narrowing it down to 4 possible options is already an enormous feat of science. So there's a great new topic for small talk with strangers and dinner conversations. You're welcome. If you had control over the fate of the universe, which of these 4 destinies would you pick for it? Let us know in the comments below. The current scientific story of the origin of the universe begins with an explosion, which made space itself expand. About 15 billion years ago, all the matter and energy that today make up the observable universe were concentrated into a space smaller than the head of a pin. The cosmos blew apart in one inconceivably colossal explosion, the Big Bang. And the stuff of the universe, together with the fabric of space itself, began expanding in all directions as they do today. But there is a force at work in the universe that casts a singular shadow over this explanation. Rather than traveling in a uniform manner, that expansion is behaving strangely. Something unusual is happening at the edges, causing matter to travel away from us faster and faster the further away from us it is. Most explosions don't speed up the longer they go on. Scientists believe that dark energy is at play. But what is dark energy? Why are so many scientists sure that it's there? And what does it mean for our understanding of the universe as we know it? I'm Alex McColgan and you're watching Astrum. Join with me today as we uncover what we know of dark energy and explore some of the ways scientists are trying to understand it. Our universe is much more mysterious than it appears at first glance. Understanding the structure of this universe is something we only really began to do in the last 100 years or so. We had plenty of understanding of stars before that point, but it was yet to be discovered how far away some of those stars actually were. Scientists before then largely believed that the universe was just a single galaxy filled with stars. Although some astronomers began to spot little fuzzy patches, actually galaxies, in the sky, and postulated them to be island universes external to our own, Nothing was proven until the 1920s, when American astronomer Edwin Hubble began studying one such object for himself. While studying what we now call the Andromeda Galaxy in 1923, Hubble realized that one of the stars he was looking at was a Cepheid variable star, a type of star that blinks brighter and dimmer over the course of weeks. Importantly, it had been proven that these stars' periods were linked to their luminosity, so by measuring how regularly the star brightened and dimmed, Hubble could calculate how bright the star should have been. By comparing that to how bright it actually was, he could mathematically calculate how far away it was. Sort of like how knowing that a candle that's further away from you is dimmer than one that's close by. Suddenly, he had a ruler with which he could measure the universe. And what he found surprised him. The star he was examining was so far away, it had to exist outside of our galaxy. This opened up our understanding, but it wasn't long before another surprise arrived. Hubble noticed another strange fact. He was able to see an expanding universe. It felt like an affront, a universe almost like a mobile, dynamic, organic, and expanding entity. It was an observation so disturbing that even Einstein refused to accept it. The German theoretical physicist had just shaken the structures of the scientific foundation by proposing an unimaginable transformation to our old notions about space and time. And even then, he could not accept that the entire universe was something dynamic and changeable. In fact, he was so convinced that our universe was a static entity, Einstein set out to modify his original equations by adding an extra element to stabilize the mathematics of the universe. This addition was called the cosmological constant. For Einstein, the idea that the universe was expanding was so distasteful that he initially couldn't bring himself to accept it. And yet, time and Edwin Hubble proved his static model wrong, making a cosmological constant unnecessary. There is an effect known as the Doppler effect that says that the wavelength of radiation stretches if its origin is moving away from you and compresses if it's moving towards you. Because Hubble knew what frequencies the light from these galaxies ought to be arriving at, he could calculate their direction of travel using this Doppler effect. And he discovered that all the galaxies in the universe were moving away from us. It wasn't long before scientists realized that if they were moving away from us now, they must have once been a whole lot closer. The theory of the Big Bang was born. But another strange fact troubled scientists, one that the Big Bang couldn't quite account for. It wasn't just that the galaxies were moving away from us, they were accelerating away from us. The further away from us they were, the faster they were moving. And acceleration requires energy. Where was this energy coming from? Nobody seemed to know, but it seemed to permeate everywhere. To fill this gap in their knowledge, scientists came up with the idea of dark energy. Applying general relativity to this expanding model universe and comparing it to the latest observational data, scientists realized that the particles we could see, known as baryonic matter, made up only 5% of the universe. Somewhere out there is a shortfall of 95%. It was the only thing that made sense. Matter was congregating strangely, as if something invisible with gravity was pulling it closer together. Scientists called this substance dark matter and attributed to it 27% of that mysterious 95% shortfall. But matter was also being pushed apart. The remaining 68% of the universe had to be the energy that was responsible for that. Undetectable, invisible, but everywhere. The maths proved it. There are a few different ideas about the nature of this energy. For starters, Einstein's cosmological constant raised its head again, this time with a new application. Einstein originally came up with the idea of such a constant as a way of perfectly counteracting gravity, a push to balance its pull, to ensure the universe neither expanded and contracted. But if you start with a bigger cosmological constant, you'd get a universe that tipped into constantly accelerating away from itself, just like we see in real life. Einstein hypothesized that empty space might not truly be nothing, but that it held energy, and it could and did create more of itself. This creation of space would create more energy, increasing the pushing power as time went on. It's unclear why space would have this property though. It was more a recognition that it seemed to than an explanation. To fill the gap, quantum mechanics stepped up to the plate. Scientists of this school hypothesized that perhaps virtual particles were to blame for this extra energy. Virtual particles are pairs of atoms that simply pop into existence as a quirk of the quantum wave function that exists everywhere. They don't stick around for long, as they meet and cancel each other out again, but in the moment before their annihilation, they could, conceivably, push against things, exerting force. This theory had some experimental evidence to back it up. There is some suggestion that virtual particles do in fact exist, at least in some form, but when scientists tried to work out how much energy such particles could create, if this was happening in the vacuum of space, their answer proved to be too large. And not just by a little, by about 120 zeros. When your answer is too big by 120 zeros, there's likely something wrong with your maths. Indeed, this answer got the dubious accolade as the worst theoretical prediction in the history of physics. The third main idea is that of a varying cosmological constant. So, not really a constant at all, but rather an adjusting field, like an electrical field or a gravitational field, that accounted for this repelling force throughout space. This force was called quintessence. And it might be the fifth fundamental force of existence, if it really does exist. The problem with this idea, however, is the same as the issue with the cosmological constant. There is no explanation as to why it exists. In short, this is still a very poorly understood field of study. More information would be needed before accurate conclusions can be drawn. Spotting something invisible is naturally hard, but studying dark energy through its impact on the universe around us is already underway. Different observatories are attempting this in different ways. BINGO, the Baryon Acoustic Oscillations from the Integrated Neural Gas Observations Telescope in Sao Paulo, Brazil, is a land-based radio telescope that intends to monitor the radiation given off by hydrogen atoms in the dark patches of space between galaxies, to see if there are any unusual distributions of matter that might point to the influence of dark energy. A curious fact about the universe is that matter clusters in waves. It is statistically more likely that there is a distance of around 500 million light-years between any two galaxies than any other number. It's thought that this is to do with ripples in the early universe right after the Big Bang that have coalesced into more solid forms of matter as the universe cooled, locking those ripples into place. Seeing the gaps between such ripples, even in the darkest corners of space, could be very instructive. However, if you really want to spot dark energy's hand over time and space, you need to go big. And it's for that purpose that ESA has just launched the Euclid Space Telescope. Euclid is a wide-angle telescope with a 600 megapixel camera designed to capture visible light and infrared radiation from over a third of the sky. Euclid's mission is to survey this massive patch of sky with a level of detail and sharpness that's 4 times greater than previously achieved by ground-based telescopes. It wants to map everything, going back 10 billion years. The hope is that in so doing, it'll be possible to create a 3D map of the influence of dark energy, with the capacity to see how dark energy's influence has changed or remained constant over all that time. Euclid will also look at individual stars too, but its main objective is sheer volume. This way, the pattern of dark energy will hopefully emerge. Euclid launched on the 1st of July 2023 and has since arrived in its designated L2 Lagrange point. It has already started taking its first images, although these photos of starscapes and galaxies are only tests and do not represent the levels of fidelity Euclid will be able to manage once it has finished its tuning. Once the calibration process is complete, however, it will begin its 6-year mission to map out our stars and hopefully answer important questions like what is the nature of dark energy and whether our understanding of the laws of gravity is really complete. So, fingers crossed that this mission can shed some light on the mystery that is dark energy. For now though, this enigmatic force remains a mystery. It's only because of the universe's expansion that we are aware of it at all. It is otherwise undetectable. But as it makes up over 60% of all that exists in the universe, it must be around us all right now. It pushes on us, just as it pushes on every other galaxy. And slowly but surely, it forces all things apart. Perhaps one day, thanks to dark energy, the only galaxy we will be able to see is our own. All others will have been pushed out past the limits of detectable light, and then there truly will be only a single galaxy in the universe, at least as far as we can see. One day, we may wonder where all the other galaxies have gone. Perhaps we will question if they ever existed at all. Whether the universe eternally expands or whether at some point dark energy will run out, we don't know. But at that point, there would be nothing but gravity, leading to everything compressing back in with a big crunch. What is dark energy? For now, only time and possibly a space telescope called Euclid may tell. Was our universe designed to be hospitable to life? In a recent Astrum video, we saw that there is more dark energy in the universe than the energy from every single atom and particle of ordinary matter combined. Yet, everything we know about particles, fields, and quantum mechanics seems to suggest that this apparently large amount of dark energy could have been, and statistically should have been, much, much larger. Decades before astronomers even had any observational evidence for the existence of dark energy, physicists were shocked to see that the most successful theories of the 20th century predicted a level of dark energy so high that stars and galaxies could never have come to exist, let alone life and humans. So, how did the universe avoid this fate? And how are we alive to even ask these questions? I'm Alex McColgan, and you're watching Astrum. Join me today as we continue to learn about the effects of dark energy on the cosmos and explore the maths that claims we really shouldn't have existed at all. One of the first things you might learn in a physics class is that gravity is an attractive force between two objects, whose strength is proportional to each of their masses. Gravity keeps planets locked in orbit around the Sun. It keeps stars grouped together in the Milky Way, and it even attracts galaxies together to form galaxy clusters and superclusters. But if we zoom out further, this gravitational attraction begins to act in reverse, causing galaxy clusters to accelerate away from each other rather than drawing each other in. So, what's going on here? Einstein's theory of general relativity gives us a lens through which we can understand this strange behavior. In general relativity, space isn't just some background in which other things can move around. Instead, space itself can stretch and warp and evolve over time. Einstein showed that in this framework, gravity is no longer a force, but rather a distortion of an object's inertial path in a dynamical spacetime. For example, when a planet orbits around the Sun, in Einstein's description, it's merely following a straight line path in a curved space. This means what we observe as a repulsive force between galaxy clusters should really be thought of as an accelerated stretching of the space between them. But what could possibly cause the expansion of space to accelerate like this on the largest scales of the universe? To begin to answer this question, we need to know what causes space-time to stretch and warp to begin with. In Newton's theory of gravity, all objects with mass exerted a gravitational pull. And in general relativity, all objects with mass curve the space-time around them. But Einstein showed that in addition to mass, any form of energy or pressure will also influence the dynamics of space-time. Energy density is how much energy is found within a given volume, how much pop, heat, zap, and motion exists within a given space, and in our universe has always been found to be positive. Pressure is how much force over an area the contents of that space sends pushing into the rest of the universe around it. Think interstellar dust pushing on each other whenever they bump into each other in the void. As you can imagine, for objects so far apart, this pressure value hovers a little over 0 on a cosmic scale. When these values are cumulatively positive, as in the following formula, their influence on the space around them causes the space around them to contract in. Essentially, they create gravity by decelerating the stretching of space. However, conceivably, if you were somehow to set the values of this equation so that pressure was negative and greater than the positive energy density, that minus sign would cause the whole thing to flip, and you would accelerate the stretching of space. In effect, you would end up with a volume of space filled with a kind of anti-gravity, a dark energy. It's a little nebulous, as it's tricky to visualize anything with a truly negative pressure. How can you have less than 0 atoms in a patch of space, after all? But atoms are not the only thing that exerts pressure. After all, pressure is simply a force applied across an area. Fields can also apply forces. Think a magnetic field, dragging a piece of iron in towards a bar magnet, or 2 magnets pushing each other away. If dark energy was some kind of field that pushed away not just other magnets, but everything, then this would match what we see the universe doing. Vacuum itself having dark energy and enough of it to slowly, very gently push the universe apart. Scientists have thought a lot about dark energy over the years and have even figured out what its combined energy density and pressure needed to be to create the rate of spatial expansion that we witness. It's around 10 to the power minus 9 in SI units, which is a very small number, which is why we don't notice it here on Earth, and only spot it on the grand cosmological scale of the universe. This is actually good news, because it turns out that if the number was much higher or lower than this, things would get very bad for our chance of existing. Let me show you what I mean, with a quick sketch of the history of the universe. Here is the full history of the universe from the moment just after the Big Bang to the present. This is the dark energy density measured by astronomers. Scientists believe its negative pressure has kept this density roughly constant for billions of years. This is the density of ordinary matter in the universe, which has little to no pressure. The density decreases over time because the expansion of the universe dilutes the matter within it. Finally, this is the density of radiation in the universe, including photons and other extremely light particles. The positive pressure of radiation makes it dilute away even more quickly than ordinary matter. Towards the beginning of time, for a very short period, there were no atoms. Very quickly though, protons and neutrons fused together to create the first atomic nuclei in the very early universe. Shortly after matter took over as the dominant form of energy, the universe cooled down enough for those nuclei to attract and hold onto electrons, forming the first atoms of hydrogen and helium. These atoms were the building blocks of the very first stars, and these stars were pulled together by gravity to form the very first galaxies and clusters. Only later did dark energy take over triggering the accelerated expansion of space and preventing the formation of larger structures. But what would have happened if the energy density were larger? Consider what would have happened if the pushing force of dark energy were stronger. It could have been enough to halt the formation of those early galaxies, pushing apart stars more powerfully than their own gravity could pull them together. A bit larger than that, and it would have been much more difficult for any stars to form either. And if the dark energy density were large enough, we would hardly have had any atoms or even nuclei produced in the universe. So that's what it could have been. What should it have been? Using some clever maths and the principles of quantum field theory, scientists attempted to predict how much the energy density of dark energy ought to have been. Their result was larger than the result we see in nature. How much larger? Their value came in at an astounding 10 to the power 45 joules per cubic meter. So, where does the predicted energy density of 10 to the power 45 joules per cubic meter fall on this graph? It's quite literally off the charts. If that prediction were correct, the universe today would have no structure, no features, no life. It would be a giant void filled with nothing but dark energy. And if the dark energy density were instead a negative 10 to the power 45 joules per cubic meter, the fate of the universe would be no more promising, as it would be forced to rapidly collapse in on itself in what's known as a big crunch. Scientists have attempted to account for their number being so far off by hypothesizing that there exist particles with positive energy and negative pressure, as yet undiscovered, that even out the maths and brings the answer for dark energy density back down towards zero. Perhaps there is some massive negative potential energy source that evens all the maths out, a cosmic stretched spring that somehow reins in all that rampant energy. Either that, or quantum field theory is fundamentally wrong. But as there's actually quite a lot of evidence supporting quantum field theory, it seems imprudent to completely throw the idea out. Instead, we are left contemplating the marvelous nature of this cosmic coincidence. What were the odds that the energy density of dark energy would be so low when it was predicted to be so much higher? That this great universal balancing act occurred in such a way that we weren't torn apart or crushed into a singularity. Without it being so low in magnitude, we wouldn't exist. Our very atoms would have never come together, torn apart by surging, expanding space. According to our predictions, we have got very lucky. This coincidence happened in such a way that the universe was able to produce life. So, was it a coincidence? The answer to that question strays from what we know for sure into what we simply theorize, however. It wanders into the realms of multiverse theory and mankind's quest to understand if we are not here by chance, but by design. There's a lot to cover, too much to cram into the end of this video, and so to do it justice, I've split this one into two. I'll cover the rest when I have the time to do it full justice. In the meantime, what do you think? Our existence so far appears to be excessively fortunate. How do you think it happened? Leave your answer in the comments below and see if other people's ideas match or contrast with your own. It's always good to hear from other viewpoints, particularly for a subject where there aren't clear-cut answers. You never know what you might find out. Our existence is surprising. Perhaps that means the universe has more surprises in store for us, if we can only find the answers. Are you feeling lucky today? You should be. If it hadn't been for a coincidence so great that it should never have happened in more than 10 to the power 56 universes, you would not exist today at all. According to our best physics predictions, dark energy density ought to have been high enough that stars and atoms would have been torn apart from its strength, unable to coalesce through gravity. Stars shouldn't exist, nor should planets, nor should you. As it happens, the actual density of dark energy is much, much lower, to the point that allowed us to exist, which is a fortunate coincidence, and raises the question, was this truly chance? Some argue this hints at the existence of a god, or an alien race so advanced that they might as well be gods, who created the universe and set its values in just the right way so that life would arise. But in physics, another theory has developed, one that says the best answer to this great cosmic enigma is the existence of multiverses. Does your being here prove that multiverses exist? Why do some physicists believe this idea? And what might other universes look like? I'm Alex McColgan and you're watching Astrum. And in the second part in this series, it's time to jump fully into multiverses. At least the topic of them. In our last video on this topic, we laid out the foundation of what is known as the cosmological constant problem. It notes that some force, dark energy, is prevalent enough that in our modern day, it overpowers gravity on a grand scale and is causing our universe to expand. This dark energy density is at a convenient level. If its density, tied to something known as the cosmological constant, was much higher or much lower, then our universe would either have been ripped apart by dark energy gone rampant, or would have collapsed down to a singularity due to unopposed gravity long before life had a chance to get going. The problem in this is that our quantum models predict that the density of dark energy really ought to have been higher. How much higher? Somewhere between 10 to the power 56 and 10 to the power 120 times higher than it is. That's more than a little off. That's so far off, it's been called the worst theoretical prediction in the history of physics. But the quantum field model is very correct in other ways, whether it's the double slit experiment with a single particle or the Bell equality test. Quantum physics turns out accurate predictions for some of the weirdest effects that we see in our universe. So how do we account for this discrepancy? Those of a religious mindset would point to the idea of intelligent design, that this wasn't so much luck as intent. A god, or extremely advanced being, has set the value of dark energy density to be just right for life to come into being for the purpose of creating us. Of course, this idea doesn't sit well with everyone. The existence of a god-like being by nature is difficult to prove or disprove, and taking such matters on faith is not really what science is about. For many scientists, a different sort of answer was needed. This is where multiverses start to come in. Let's go back to 1987, when the precise value of dark energy density in our universe had not yet been measured. But it was clear that it was extremely small, or zero, since, well, we existed, and so did everything around us. That year, physicist Steven Weinberg published a paper connecting the universe's fortuitously low dark energy density with something known as the anthropic principle. Essentially, the only universes that we can evaluate the probabilities of are the universes that met the right conditions to produce us. If the universe hadn't rolled such an unlikely roll of the dice, there would be no us to say whether these things were more or less probable. If it takes a massively unlikely roll of the dice to produce humans, then a universe where that roll of the dice actually happened is the only universe we could possibly see. Weinberg could be more specific than that. He was confident that the threshold of dark energy density for forming life would be no lower than the threshold for forming galaxies. In other words, by the time galaxies have formed, you've probably crossed the threshold to where life can form too. After all, How else was life supposed to arise if there were no stars and galaxies to provide complex building blocks and energy? At the time of his publication, observations of an extremely old and distant quasar had indicated that galaxies had already begun to form just 1 billion years after the Big Bang. Weinberg used this information to calculate that the formation of these ancient galaxies required the dark energy density to be smaller than around 10 to the power -7 joules per cubic meter. That meant that, assuming the galaxies were indeed necessary for life to arise, the threshold dark energy density for life to exist was less than or equal to this value, while not being so low as to be negative. Weinberg initially reasoned that if the dark energy density was significantly smaller than this value, something else other than anthropic reasoning must explain the dark energy density smallness. However, as we now know, the real dark energy density is closer to 10 to the power -9 joules per cubic meter, which isn't too far off from the threshold of 10 to the power -7 calculated by Weinberg. In short, life and dark energy density correlate surprisingly well. Of course, this ignores one vital point. Just because we can see universes where we exist doesn't mean it is guaranteed that we should exist. We could have just not existed at all. After all, the odds of the cosmological constant being at its recorded level is incredibly unlikely. Could the various contributions to the dark energy density have cancelled out to a value compatible with life just by chance? Probably not. Here's what would have needed to have happened. Just imagine generating 3 random real numbers between -1 and 1, adding them up, and hoping that the magnitude of the sum is at most 0.0000 with 55 zeros 1. It sounds just about impossible. But what if we had more than one go at it? What if we could generate those numbers over and over and over again until we got lucky? It might take us something like 10 to the power 56 tries, but given enough time, the unlikely cancellation of 3 randomly generated numbers will turn into an inevitability. We can use the same logic to potentially explain why the dark energy density is so bizarrely small. Instead of just one universe, imagine there exists a vast multiverse, with each universe having a different, random value for the dark energy density. Only a tiny fraction of them would have a dark energy density small enough to be compatible with life, but that's exactly where we humans would expect to find ourselves. This explanation requires no coincidences, no fine-tuning, no intelligent design, just a lot of different universes. On its own, the idea of a multiverse would still be too vague to be good scientific theory. For starters, what kind of multiverse are we talking about? How do they exist in the first place? Fortunately, there are actually a few different concepts of multiverse that physicists can describe. Firstly, we have a multiverse separated by time. If you are familiar with the idea of the Big Bang and the Big Crunch, you will know that it's often believed that this creation and destruction of the universe is an eternally repeating process, with new universes arising each time. If the underlying numbers of each universe are a bit different with each iteration, for instance, if dark energy density can change from universe to universe, then with enough Big Bangs and Big Crunches, you could inevitably end up with a universe with a dark energy density exactly like our own. There are a few assumptions at play here, of course, as we don't know for sure that the universe does contract into a Big Crunch yet. But if it does, and if the rules of the universe are a bit different with each new iteration, then this is a viable model for a multiverse. A second multiverse described by physicists, although one I find personally a little bit more iffy, is a multiverse separated by space. While the rules of physics seem to be consistent across all of space that we can see, there are realms of space beyond our sight, sections of the universe that are accelerating away from us so quickly we will never see light from them. It's conceivably possible that the rules of these parts of the universe could differ from our own. And if this occurs, then we are essentially in another sort of multiverse. I find this model a little less satisfying though, both because it feels strange to call a further away part of our universe a different universe just because we can't see it, and also because there is no evidence that the laws of physics differ across space. This seems to me to be the least likely sort of multiverse. But finally, modern physics describes a third type of multiverse, one that is disconnected from our space-time entirely. In the many worlds interpretation of quantum mechanics, every macroscopic interaction or measurement of a quantum state causes the wave function of the universe to branch into multiple non-interacting parts. If you've heard of Schrödinger's cat, you can imagine the universe splitting into one universe where the cat is alive and one where the cat is dead. With every such interaction, the total number of universes grows exponentially, and the quantum multiverse becomes even richer and more diverse in its features. To be clear, we still don't know whether this branching process is the correct physical description of quantum mechanics, but it is arguably the simplest, and it is perfectly consistent with all experimental data. Or rather, we have no proof that it doesn't exist that way. If it does turn out to be correct, then it would add a whole new layer of complexity to our understanding of the multiverse. Multiverses are useful in that they remove the need for massive coincidences or intelligent design as a way of explaining our presence in the universe. However, are they actually real? Unfortunately, the answer is an unsatisfying "we don't know." While differing multiverses do help solve the cosmological constant problem, we actually have no evidence that they exist beyond the offering of an explanation for that coincidence. We have no proof that the laws of physics change across space or time or quantum universes. If other universes exist, they might have exactly the same laws of physics and values for dark energy density as our own, which would put us right back in the same problem we started with. How are we here when the odds of the galaxy itself existing is 10 to the power 56 to 1? And getting that proof will be difficult. We will need to either survive through a big crunch, or pass into a part of the universe that's so far away that not even light can travel quickly enough to get back from it, or enter a different quantum universe somehow. All seem impossible, or at least very difficult, and potentially the kind of trip you can't return from. This might be just as unprovable as the existence of God. So, in a way, you are free to believe whichever you find most comforting, or perhaps continue to wait until a better way of answering the question can be found. What is undeniable is that we are here. We live, we breathe, we can experience all the joys of life. However that came about, that's something to be incredibly grateful for. If we keep striving, perhaps we can one day discover the secrets to our origins. Whether we got incredibly lucky, did an all-powerful hand guide us into being, or was it the rolling of infinite dice that caused an inevitable result? Believe what you like. Just don't let it stop you from appreciating the wonders all around you. We don't need there to be a multiverse to appreciate this universe we're in, after all. Stars are some of the most beautiful and awe-inspiring objects in the universe. Through violent thermonuclear reactions, they emit enormous amounts of light, illuminating the night sky and heating up any nearby planets in the process. Through mergers and powerful explosions, stars are also responsible for producing the heavy elements that make up much of the matter we see around us. Astronomers and astrophysicists have come a long way toward understanding how stars operate, to the point where we can even predict how long it will be before our sun runs out of fuel and transforms into a red giant. But today, we're not just going to talk about the types of stars we're familiar with. Instead, we're going to contemplate stars we've never seen before. ones that astrophysicists say could hypothetically exist, including ones that are quite literally made of vacuum. I'm Alex McColgan, and you're watching Astrum. Join me today as we dive into the world of exotic stars. Some of these stars can mimic black holes and resemble dark energy, which is why they have been the subject of many recent studies and even some sensational drama in the world of physics. In this video, we're going to explore all of it, from the physical theories at the core of these ideas to the wildest speculations surrounding them. First, we need to lay some groundwork and understand how stars work in general, starting with the most important star of all, the Sun. Since the Sun is made of gas or plasma and not solid matter, you couldn't stand on its surface like you would on the Earth. The Sun's gravity would pull you down toward the center. So why doesn't the gas at the surface get pulled inwards too? It turns out that there is a pressure pushing outward from the Sun's core that counterbalances this pull of gravity. The main source of this pressure is the radiation created by fusion reactions in the core, the same radiation responsible for carrying light and heat from the Sun to the Earth. Whether you think of radiation as individual photons or waves in the electromagnetic field, its path from the core towards the outer layers of the Sun will cause an outward push in all directions. This radiation pressure wouldn't be enough to stop you from falling into the Sun, but it's just enough to stop the Sun's own gas, which is relatively light, from collapsing in on itself. This balancing act between inward pulling gravity and outward pushing pressure is a feature of pretty much all known types of stars. What differentiates different types of stars is where that pressure comes from. For our Sun, the pressure comes from fusing hydrogen into helium. When the Sun runs out of hydrogen in about 5 billion years, it will become a red giant star and begin to generate its pressure by fusing helium into even heavier nuclei like carbon and oxygen. Eventually, the Sun will also run out of helium and any other light elements that could be used for fuel for nuclear fusion. At that point, it will collapse into a small star known as a white dwarf. Since no more fusion is occurring anymore, white dwarfs are sometimes called stellar remnants instead of stars. But if there's no more fusion, where does the pressure to support these stellar remnants come from? It turns out that gravity pulls the gas of a white dwarf inward until it's so dense that a new type of pressure emerges, known as electron degeneracy pressure. This is a purely quantum mechanical effect, and it's the same effect that's responsible for you not being able to pass your hand through solid objects. Electrons simply cannot get too close to each other without an extraordinary amount of energy. But some stellar remnants are so massive that even electron degeneracy pressure isn't strong enough to counteract the pull of gravity. This is called the Chandrasekhar limit. It's absolutely impossible to have a stable white dwarf any heavier than 1.4 times the mass of the Sun. If a star has burned through all its nuclear fuel and its core is still heavier than the Chandrasekhar limit, that core will collapse in on itself until it becomes so dense that an even stronger type of quantum pressure emerges, known as neutron degeneracy pressure, which, as you may have guessed, prevents neutrons from getting too close to each other. A star that reaches this state is called a neutron star, the smallest and densest known class of stellar objects. So now you might be wondering, is there a maximum mass that a neutron star can have while still being supported by neutron degeneracy pressure? And there is. This time it's about 2.2 times the mass of the Sun. Any heavier than that, and the neutron star would keep collapsing under the influence of its own gravity until, well, actually, not until anything. As far as we know, neutron degeneracy pressure is the strongest possible pressure that ordinary matter can exert, so there's nothing left to prevent a sufficiently heavy stellar remnant from collapsing in on itself forever. This is the fate that might await some of the most massive stars we've observed in the universe. From the perspective of an outside observer, these stars would get so dense that all we'd be able to see is a black hole. But then scientists started to wonder, what would happen to a star that wasn't made of ordinary matter? If exotic forms of matter could hypothetically produce even larger pressures than neutron degeneracy pressure, then what new kinds of stars could exist? You might think that we could just continue the pattern that we were starting to see earlier. Stars could get even smaller and even denser than neutron stars, as long as they were supported by some even greater pressure. You might think that the only limit on how small these stars would get would be the point of no return, where they would turn into black holes. That point of no return is when a star becomes smaller than its own Schwarzschild radius. This is almost true, but not quite. Instead, physicist Hans Adolf Buchdahl showed in 1959 that a star made of any realistic form of matter with positive energy density and pressure can't be smaller than 9/8 times its Schwarzschild radius. It might not sound like a big difference, but that factor of 9/8 means that any realistic star has to be noticeably larger than a black hole, making it much easier to tell them apart. That's when physicists began asking about stars that Buchdahl would call less realistic. For example, what if a star was made of matter that allows for pressure to be negative in some regions and positive in others? Then Buchdahl's limit wouldn't apply, and that star would be less than 9/8 times its Schwarzschild radius. In fact, it could be arbitrarily close to the size of a black hole with the same mass. As a side note, theoretical stars like these that could mimic the appearance of black holes came to be quite a nuisance for astrophysicists, since now every time they discovered something that they thought was a black hole, they couldn't just say they discovered a black hole. They had to qualify that it's either a black hole or an extremely compact object mimicking a black hole, even though in their hearts most of them are quite convinced that it's a black hole. But back to the main point. What would these exotic stars with negative pressures even look like? The answer turns out to be even weirder than you might have guessed. Tolman, Oppenheimer, and Volkov derived an equation in the 1930s that describes how the pressure of a stable star changes as you go outward from its center. These days, it's just called the TOV equation for short. If the center of a star has a significantly negative pressure, which would exert some sort of attractive pull instead of a push, the TOV equation says that this star can only be stable and in balance with its own gravity if its pressure does something really wonky. First, the pressure has to blow up to negative infinity somewhere in the star. Then it has to flip sign to positive infinity and decrease outwards from there until it reaches zero pressure, marking the star's outer surface. The exact location of the infinite pressure depends on what the pressure is at the center. So if you tune that central pressure just right, you can keep the pressure finite right up until the edge of the star. That happens when the pressure at the center is exactly equal and opposite to the star's energy density there. In this special case, the TOV equations say that the pressure and energy density remain constant, equal, and opposite throughout the entire volume of the star right up until its surface. If you've seen some of our other episodes, this might ring a bell or two. A constant positive energy density paired with a constant but negative pressure. That doesn't sound like any star we've seen before, but it's starting to sound more like a mysterious component of our universe: dark energy. And since the pressure and energy density in a gravastar are equal in magnitude, it's not just any kind of dark energy. Those are the exact properties of vacuum energy. That's why this special exotic star came to be known as a gravitational vacuum star, or gravistar for short. Inside of a gravistar, there is precisely zero gravitational force, because the positive energy and negative pressure respectively exert a gravitational pull and push that cancel each other out. And since the pressure in gravistars is constant, there is no pressure gradient to exert any sort of push in one direction or another either. This means that if you found yourself inside of a gravistar, you would neither be pulled in nor pushed out. You could float freely, just as though you were in a real vacuum. Another curious feature of stars with negative pressures is that the closer you get to the special limit of a gravistar, which, if you recall, is when the infinite pressure surface gets pushed out to the edge of the star, the more their size approaches that of a black hole with the same mass. This raises two key questions that have recently gotten a lot of attention from physicists. First, how can we tell whether the extremely compact objects astronomers have observed in merger events and at the center of large galaxies are black holes or just exotic stars with nearly the same size? And second, if gravistars are real and scattered throughout the entire universe, then could they be the dark energy that's been making the universe accelerate for the past 5 billion years? To answer the first question, physicists rely on the main distinction between black holes and other compact objects, the existence of an event horizon. You see, the defining feature of a black hole is that nothing that falls inside or even touches the surface of a black hole can ever come back out. On the other hand, if an exotic star is even slightly larger than its Schwarzschild radius, it would not have an event horizon, and it would potentially be able to emit information outwards in the form of light. Not only that, but objects without event horizons could have different signatures in their gravitational wave emissions than those of black holes during a merger. This would allow us to tell them apart by measuring and analyzing those gravitational waves using observatories like LIGO. But even with this battery of tests, it turns out sufficiently small and dense stars can still be difficult to distinguish from black holes. So far, the best we can do is to say that the radius of the black hole candidates we see in the universe is at least approximately equal to their Schwarzschild radius. In some cases, that's just a rough estimate, but in others, we've calculated that radius to within 40 decimal places. As for the second question about dark energy, that's where things get really heated. In early 2023, an analysis led by physicists at the University of Hawaii found that astronomical observations of massive black holes showed them to be growing in mass over time at exactly the same rate that dark energy would be expected to grow over time due to the expansion of the universe. They came to the inevitable conclusion that black holes must be made of dark energy, and that they are really more like gravistars than ordinary black holes with infinite density singularities at their centers. This conclusion was fiercely contested. Astronomers came out arguing that the analysis of the observational data wasn't quite right, and theoretical physicists came out arguing that the expansion of the universe should have nothing to do with the growth of black holes in any case. So while the idea that dark energy could exist in the form of gravistars sounds exciting, it looks like the scientific community isn't going to be convinced unless it's simultaneously supported by better data and more compelling theoretical models. But where do you fall in this debate? If it walks like a black hole and talks like a black hole, should we just call it a black hole? Or should we consider the possibility that black holes could really be secret troves of dark energy? Let us know your thoughts and questions in the comments below. Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, Click the link to this playlist for more Astrum content. I'll see you next time.